Okay, Algebra 2 students, we are getting ready to get into a new unit, Unit 5. This unit is going to be all about parabolas and quadratic equations, how to work with them, how to solve them, how to read them, what their solutions mean, all of that kind of stuff. It's going to take us a number of weeks to actually get through all of this. So as a result, we're going to do like we did in Unit 2. We're going to break the unit in half. We will do some of the information before Christmas break and have a test, and then we'll finish up the rest of the information after Christmas break and then have a different Unit 5 test. Okay, but before we can really get into the quadratics, we need to have a discussion about what are called imaginary numbers. Our objective is the student will learn about the nature and mathematics of imaginary numbers. I anticipate these will be the notes for the first class where all of the Algebra 2 classes get to meet. That'll be Thursday following Thanksgiving break. Not sure about what the date is for that right off the top of my head, but that's when I think these notes will be due in class time. As always, hit pause anytime you need more time to copy things down, and press play when you're ready to move on. Okay, now all numbers that we deal with in mathematics fit into one of two categories. Now, there are the real numbers, okay, which are the numbers that we work with pretty much on a daily basis. I would probably venture a guess and say 100% of all of the information, all the problems, all the answers that you've worked with up to now in mathematics have been in the real numbers. The other side of that discussion is the imaginary numbers. Now, we've dealt with the real numbers a little bit this year, so you're probably already familiar that the real numbers have a set notation, and the set notation for real numbers is the capital R. Imaginary numbers have a little notation as well. It is an italicized lowercase I. If you think back into your time of mathematics, you've probably might have noticed that I is never used as a variable in a problem. We said unknown values can be anything, X, Y, Z, P, Q, A, B, C, I mean any kind of letter. But you'll probably, if you think about it, notice that I has never shown up as one of the variables. And the reason for that is because I has a special meaning. Okay, so we know a lot about the real numbers. These are the numbers that show up anywhere on the number line. And that's not to say that these are only the values that get labeled on the number line or anything like that. Real numbers are they're whole numbers, they are decimal points, they are fractions, they are positive, they are negative, they are zero. Okay, anything that can be pinpointed anywhere on our standard number line, those are the real numbers. So the vast majority of the problems that we work with have answers found in the real numbers. There is only one occurrence that may ever arise that will cause a value to become part of the imaginary numbers. And that occurrence is running into a situation where a negative is going to be stuck underneath a radical in such a way that it cannot be simplified out of the problem. Now, having a negative underneath a radical by itself is not a big deal. Lots of times we will see negatives, okay, in the form of either negative values or subtraction signs, but either due to the algebra that's going on underneath the radical, or perhaps the math around the radical itself can cause the negative to be simplified. But after all the math and magic tricks are done, if the negative is still stuck and cannot be moved, then our answer becomes imaginary. What you're going to see is that this is one of the first conceptual failures in mathematics that we will come across. I know at this point in time, y'all probably believe that humans have a pretty good grasp of the mathematical world, that we understand everything that there is to understand. Okay, but unfortunately, that is not correct. A lot of the things that we believe in the way that we understand mathematics simply do not work. That there's a problem, and our human brains are just not strong enough to be able to undo what is going wrong. And this is going to be one of those times. Now, the problem that I'm referring to stems from this. Our general rule and understanding for mathematics is that for every operation that is out there, there is an opposite operation that will undo it. Okay, this is how we have lived through our last 2.5 years of mathematics, moving things from one side of an equal sign by doing the opposite of whatever's already being done. For example, if something is already being added, we can always subtract it in order to undo it and move that thing to the other side of the equal sign. Same rule is true, okay, with multiplication and division. Okay, if something were being divided on one side of the equal sign, we could always eliminate it and move it to the other side by multiplying, because those were opposite operations. And the same is largely true for things like squares and square roots. Okay. However, this is kind of step number one. Okay, when there are things that we can actually do to one side of a problem that can damage that problem to the point that it cannot be repaired. Okay, so it's kind of, we're doing what we're trained to do, but due to no fault of our own, the nature of mathematics actually interrupts the problem in such a way that it cannot be restored. Okay, so what we're going to do is we're going to take a quick look at the squares and square roots as far as these opposite operations. Okay, so let's take a value like -5. Okay, if we were to take a value like -5 and square it, okay, we would get +25. Okay, because obviously 5 times 5, and that's what squaring something means, to multiply it by itself. 5 times 5 is 25, and a negative times a negative we know is always going to be positive. Okay, now we just committed, not committed, but we just enacted some type of an operation. Okay, so we squared something, so we ought to be able to undo what we just did by doing the opposite of squaring, which would be square root. Okay, so if we take our 25 that we now have, and we take the square root of 25, which is looking for a value times the exact same value that equals 25, clearly that would be 5. 5 times 5 is 25. The problem is what just happened to the negative side. We began with -5, we squared it, and then we undid the square by square rooting it, and we ended up with a different value than we started off with. Okay. Now, we did not do anything wrong. There was nothing wrong with our math. Our concepts and our strategies were good, but it is the nature of mathematics as we understand it that causes this failure. This is just something that we do not entirely get when it comes down to the mathematical universe. We have not figured this one all the way out. Okay. Imaginary numbers are part of the summary that is going to help us describe this situation. As you'll find in math, when we run across these situations where we cannot get a full grip on what exactly is happening, in the meantime, while we understand that we do not understand what we're seeing here, a lot of times in those instances, what you're going to find is we have a value or a definition that is assigned to describe this problem. Okay, and imaginary numbers are one of those descriptions. Okay. So the rule here is, okay, I, which is an imaginary number, is equivalent to the value of the square root of -1. Okay, so we don't understand why a value ought to have a negative underneath a radical. We understand that the math of this situation is going to fail us. Okay, but until it gets figured out, until another Albert Einstein or somebody like that comes along and it comes up with something brilliant that solves the problem for us, we have a value that is assigned to it, and that value is I. Okay, now let's take a look at a couple of examples here that deal with I in the problem. Okay, as always, you should remember from your discussions of the Pythagorean theorem, not only back in junior high, but hopefully in geometry as well. Okay. And when you simplify a radical, it takes 2 of a factor underneath a square root to join together to come outside of the radical. Okay. So hopefully we've done things like the square root of 9 plenty of times before. In order to simplify the square root of positive 9, we know that 9 factors down into 3 times 3. But there's also a negative underneath that radical. Okay, so the way that we factor that is to actually consider the negative as a -1 that lives underneath the radical with the 9. Okay, so we have a -1 times a positive 3 times a positive 3. That is -9 factored. But as we said, it takes 2 of a factor underneath the square root in order to join together to come outside of the radical. That means we're looking for 2 of stuff. Well, we have 2 3's that are underneath the radical. Those 2 3's underneath are going to join together and come outside of the radical, and they will make a single 3 outside of the radical. That will leave the -1 underneath the radical. Well, we have a value that is assigned to the square root of -1, and that value is I. Okay, so the 3 gets to come outside. The square root of -1 is left, but that translates into I. So the square root of -9 simplified is 3I. How about the square root of -12? Well, how does 12 factor? 12 actually factors a couple of different ways. You can break it down into 2 times 6, or you can break it down into 3 times 4. Okay, but in either case, either the 6 of 2 times 6 is not finished yet. It would be 2 times 3. Or the 4 of 3 times 4 is not finished yet. 4 would break down into 2 times 2. So 12 is going to be 2 times 2 times 3. And the negative in there is going to be a -1. Okay, so -1 times 2 times 2 times 3, that is -12 factored. We're looking for pairs of stuff. Obviously, you have a pair of 2's, so the 2's are going to join together and come outside. The 3 does not have another 3 to join with, so it's going to be stuck underneath the radical. But the -1 is going to get to come out in the form of I. So we will get a 2 outside of the radical, we'll get an I outside of the radical, and we will get a 3 still stuck underneath the radical. Anytime you see a negative underneath a radical, you are going to have to simplify it. It's one of those things that's considered bad format in math to leave a negative underneath a radical. So you will always simplify it out by bringing the I outside of the radical. Okay, now I'm going to give you a little bit of information here. Go ahead and write this part down. I'll tell you where you can take a break here in just a second. Actually, imaginary numbers can appear in 4 different formats. We will see I raised to one of 4 powers. Okay, I to the first, I squared, I cubed, and I to the 4th. Okay. Now, if we break this down by the laws of exponents, of course, I to the first is simply 1 is just an I. I squared is I times I cubed is I times I, and so on. Okay. Now, we know that I has a value that is assigned to it. It is the square root of -1. So if we were to convert all of these i's into square roots of -1, we would have this. Okay. Now, some of this, like the I to the first, is simplified as far as it can go. The other three on the right hand or the right part of the screen have more that can be done. Okay, the basic rule with radicals is a square root can combine with another square root by multiplication by the values underneath the radical simply joining together underneath a large radical like we've done here. So instead of I squared being the square root of -1 times the square root of -1, it can be the square root of -1 times 1. Okay. Now from here, if you look at I squared, you can see that we have two -1s underneath the radical, and that's what we want to be able to join together to come out. So in I squared's case, the -1 and the -1 are going to join together. They will come outside of the radical to make a -1 outside, and there will be nothing left underneath the radical, and so it will vanish. On I cubed's case, we can get a pair of -1s out, but there will still be a -1 left underneath. On I to the fourth case, we can get a pair of -1s out of the radical, but then we can get another pair of -1s out of the radical. That would bring us to this information. I squared is now at -1. I cubed is at -1 times the square root of -1. And I to the fourth is at -1 times -1. Now I squared is simplified as far as it can go. I cubed can be cleaned up slightly. There's no reason to say I have -1 square roots of -1. The one outside of the radical can actually be dropped and just say negative of the square root of -1. And on I to the fourth, -1 times -1 is +1. Okay. Now all four of these values are now simplified as far as they can go. Okay. These are the values for I to the first, I squared, I cubed, and I to the fourth. You absolutely need to have these guys copied down and marked, okay, because these are what the values translate into, and you will run into problems over the course of the years that will ask you to write down these in I form or in radical form. So you need to know these conversions. Now, some of you may be wondering, hey, wait a minute, I to the first, I squared, I cubed, I to the fourth, those are not the only exponents that may show up in a problem. What about I to the fifth? What about I to the 18th? Stuff like that. Okay, well, I'm going to answer that for you on the next slide. Okay, and I'm going to say you don't need to particularly copy this one down, just please keep tuned in and listen. Okay, we have our four values of I to the first, I squared, I cubed, and I to the fourth, and they are listed at the top of the screen just like they were at the bottom of the last screen. Okay, but there's also I to the fifth. Now, if we were to take I to the fifth and break it down like we did on the last screen, turn it into 5 i's, turn those 5 i's into square roots of -1, and so on, in the end, what we would find is that it simplifies all the way down to the positive square root of -1, which is exactly the same as I to the first. On the next one, I to the sixth, if we did the same thing, 6 i's, 6 square roots of -1, and simplified all the way down, what we would end up with is a negative value 1, okay, which is exactly the same as I squared. And if we were to do it to I to the seventh, we would find it to be the same as I cubed. I to the eighth would be the same as I to the fourth. I to the ninth would be back to being I to the first. I to the 10th. Okay, should say I squared on the end there. I apologize. Let me write that in right now. This should be a 2 right there instead of a 1. I'll need to fix that in my notes. Okay, so the end game of this discussion is to point out that this is a pattern. Okay, it's what we call in the mathematical world as being cyclical, and you will run into this as you continue to go higher in mathematics, where a mathematical pattern is established and then it repeats itself and it's a cycle. Okay, so basically what you're needing to know is we can find any value for I by just deciding where that value lines up with I to the first through I to the fourth. Okay, I know the notes are long today, but just hang in there, getting close. Okay, so let's take a look at some of these values and how they match up. Now, if you've quit taking notes on me, you need to start again. Okay, to figure out how values match up, the easiest way is to divide the power you have by 4 and look at the remainder. Now that means you actually need to divide it, not go grab a calculator off of the wall and ask what the calculator thinks, because we need a remainder, not a decimal point. Okay, so we're going to simplify to the smallest power of I, and the value we happen to be working with is I to the 39th. Okay, so let's see what we can figure out here. Okay. Now, some of you also are in the habit of anytime there is an established pattern on something, instead of doing any math, you'll want to spend the next half hour writing out the pattern until you finally get to the answer. I'm going to tell you it's impractical and very unreliable to write out I all the way to the 39th power. And I say it's impractical and unreliable because chances are by the time you actually get to I to the 39th, you have probably made some type of a mistake, you have wasted a lot of time, and you are going to get the wrong answer anyway. Okay, so quit trying to shortcut, which is not a shortcut, your way around the problem. Just do the math. Okay, take 39 and divide it by 4. It's really not that hard. Okay, the division would look like this. 4 goes into 39 9 times. That would be 36. We subtract the 36 away, and we end up with a remainder of 3. It is this remainder that we are interested in. Okay, the reason we're interested in it is because the remainder you get is going to be the equivalent power of I to the power of I that you had from your previous problem. What that means in this case is that I to the 39th is equivalent to I to the third. So the remainder simply becomes the power of your answer. It's really quite simple. Now this is review from pre-algebra and algebra 1. I'm going to give it to you anyway in case you have lost it or never bothered to get it to begin with. There are 5 laws of exponents, and dealing with imaginary numbers, there is always the possibility that we may have to work with the laws of exponents because basically I represents something going on with exponents. Anyway, here's are the 5 laws. Okay, you can copy them down real quick. I will read them aloud, interpret to you. Okay, law 1 deals with the situation where you have 2 bases that are the same. In this case, x is x times x. Okay, and the law 1 says if you have the 2 bases being same base being multiplied together, then you add the exponents. Law 2 deals, instead of multiplication of the same bases, this time we're going to divide the same bases. So you have a base x being divided by a base x. Law 2 says to subtract the exponents in this order: the numerator's exponent minus the denominator's exponent. Now that may give you a positive exponent, that may give you a negative exponent. And you'll see here in a moment we have a different law to deal with a negative exponent. Law 3 deals with a situation where you might have an exponent raised to an exponent. In that case, you actually get to multiply the exponents. Law 4, okay, I mentioned a moment ago, deals with the possibility that you might have a negative exponent. The only way to handle a negative exponent is to reciprocate the base that the negative exponent is attached to. That means if that base is in the numerator, we're going to send it to the denominator. By sending it through the fraction bar from the numerator to the denominator, it's going to change the sign from negative to positive. Same thing, if the base was in the denominator with a negative exponent, we would send that base to the numerator. Passing through the fraction bar is going to switch the sign and make it positive. And law 5 deals with the possibility that you might end up with something raised to the 0 power, and something to the 0 power is always 1. Press pause if you need more time. Okay, a couple of examples and then I'll leave you alone. Okay, simplify to the smallest form of I. And we have I squared times I cubed. Okay, now by the laws of exponents, we have the same base being multiplied together, I times I. Okay, so what do the laws of exponents tell us that we are supposed to do with the exponents if the bases are the same? Law 1 says if you're multiplying the same bases together, then you should add your exponents. So I squared times I to the third, even though a lot of people are going to write I to the sixth, it's not I to the sixth, it's I to the fifth. Follow the laws of exponents, add them up. Okay, is I to the fifth, is that simplified as small as we can get it? No, it's not. That's part of that cycle. Where does I to the fifth line up with I to the first, I squared, I cubed, and I to the fourth? I fifth is the equivalent of I to the first, or we don't have to write the first power. We could simply write I. Okay. How about some values? Simplify and leave in radical form. The square root of 2 times the square root of 3. Well, as I said earlier in the notes, when you have two radicals being multiplied together, okay, the rule is that you can put it all underneath one radical and you simply multiply the values. So, but okay, first thing we need to deal with would be the negatives underneath the radicals. Okay, we can simplify the I out from underneath the radical. So instead of the square root of negative 2, we can have I root 2. And instead of the square root of negative 3, I root 3. Okay, now when we combine them, we're going to get I times I, which will be I squared, because we add up the exponents, and square root of 2 times square root of 3 is square root of 6. Now we're going to be stuck with square root of 6. It does not factor down into anything but 2 times 3. There's no pairs underneath there, so we're not going to be able to simplify it out. But what do we know about the I squared? The instructions told us to get this in radical form, not I form. So I squared can be simplified. I squared is the value negative 1. Okay, so our answer in this case would be the negative of square root of 6. Okay, the math is not difficult. It's just new information. Okay, so what I'd like you to do, okay, is copy down these three and give them a try. I apologize for the notes being long today. It's not difficult. It's just information. Okay, copy down these three examples. Shouldn't take you any more than a couple of minutes to give all three of these a try. Bring the solutions with you to class on that Tuesday following Thanksgiving, and we'll work them out together as well and see if you get the right answers. Again, I apologize for the length of the notes, and I'll see you in class.